Welcome back. In this lesson, we're going to be looking at syllabus point A1.3.4 Evaluate the use of polling and interrupt handling. Now, in the previous lesson, we looked at scheduling algorithms. There are processes which can be high priority or low priority. Now, what would happen if there was a queue of low priority processes and a high priority process occurred? How would the operating system know about it? This is where polling and interrupt handling come into play. When external events occur, the CPU needs a way to detect them and respond to them. And two main approaches used are polling, where the CPU repeatedly checks the status of a device at regular intervals, or interrupt handling, where devices signal the CPU when they need attention, which then temporarily pauses the current process. These are the two main techniques used, which you need to be aware of. However, polling wastes a lot of CPU cycles if no event occurs because you're constantly checking the status of different devices. Hard drive, are you okay? Keyboard, are you okay? Mouse, are you okay? Things like that. Interrupts, on the other hand, allow the CPU to perform other tasks until needed. This is where the keyboard will interrupt the CPU seeking its attention rather than the CPU checking on the keyboard and asking how it is. The choice depends on factors such as frequency, predictability, and latency requirements. So let's look at each of them turn by turn. First up is polling. The CPU executes a loop to check if a device requires service, and it works best when the events occur frequently and predictably. So reading sensor values in an embedded control loop, fantastic. That's where polling comes into play. It's very simple to implement, there's predictable timing, and it's good for regular high frequency events. Of course, it has disadvantages that there is a high CPU overhead. The CPU spends time checking all these devices, which means it can't do normal tasks. So it wastes a lot of time. It's power inefficient. It drains a lot of battery, especially if you're using it in portable devices, because you are spending energy checking things which might not even need to be checked. And it's not suitable for rare, unpredictable events. Interrupts, on the other hand, are signals which are sent by a particular device or even a software seeking the CPU's or the operating system's attention. The CPU will then temporarily stop the current execution, for example, whatever process is currently running on it, if it is lower priority than the interrupt. This process is called context switching. It will then call an interrupt service routine, which is a routine designed to deal with the interrupt. It will execute it, it will process it, and then it will get back to the original process or the original program. An example would be that Google Docs is running, there's nothing happening on screen. You suddenly press a keyboard key, and then the character changes on screen. So the keyboard will send an interrupt to the CPU, which currently pauses whatever it's doing for a second and deals with the new interrupt. There are a number of advantages to interrupt handling. It's efficient. CPU can perform other tasks when there are no events occurring, which is different from polling. There is low power consumption, which is very important for battery devices. You do not spend time polling devices unnecessary in consuming power. It's suitable for low frequency or unpredictable events type situations, but it does have disadvantages also. For example, this is more complex to implement. It requires interrupt vector tables, priority handling, which interrupt is of a higher priority than another. There are potential security risks because interrupts could be exploited. You could pass something simple as a high priority process, and that wastes a lot of CPU time. Overheads from frequent context switching. If events are too frequent, that can also happen. So that means the CPU will just constantly swap context. One process is offloaded, another is loaded instead of actually doing the processing. So just make sure you know that an interrupt is a signal to the processor from a device which is attached to a computer or from a software program within the computer, which causes the processor to stop and figure out what to do next. When an interrupt is received, the processor saves its current state or context and starts executing the ISR, which is the interrupt service routine to deal with the interrupt. After the ISR is finished, the processor resumes its previous state and continues its prior task. And this particular mechanism allows the CPU to respond promptly to important events, improving the system's efficiency and responsiveness. Now we can compare both of these types of techniques using event frequency, CPU processing overheads, the impact on power sources, event predictability, controlled latency, and even security concerns. So on screen, you see a table comparing both of them. The event frequency refers to how often an event actually occurs. So in a high frequency environment, interrupts are often preferred because they allow the CPU to be notified immediately when an event occurs. And this minimizes wait times and improves responsiveness. Polling, on the other hand, is suitable for low frequency events. In those type of situations, polling might be adequate and simpler to implement as the CPU can afford to check periodically without significant performance degradation. CPU processing overheads involves a lot of extra work that the CPU must do beyond its primary tasks, such as managing interrupts or polling devices. Now, interrupts can cause overhead due to the need for saving and restoring the CPU states, context switching, and executing the ISR. Polling, on the other hand, introduces overhead by consuming CPU cycles just to check if a device needs attention. This potentially reduces the efficiency of the CPU for other tasks. So if you have more devices on your system, you're continuously polling them instead of doing anything important. This also has an impact on the power source, which refers to the source of power, battery, or mains. Devices running on batteries, such as mobile devices, benefit more from interrupts because the CPU can enter a low power state or sleep mode when it's not processing interrupts. Polling, due to its continuous checking, can drain the battery faster. When you don't have power efficiency needed, you might want to go for polling in those situations when you're perhaps plugged into the mains, but on battery powered devices, interrupts are preferred. Event predictability refers to how predictable the timing of events is. In systems where events occur at known regular intervals, polling is an effective method, but in systems where unpredictable events occur, interrupts are superior. Controlled latency refers to the ability to have predictable and manageable delay between an event's occurrence and the system's response to it. So, interrupts can provide lower and more controlled latency because the CPU can respond as soon as an event occurs. Polling might introduce variable latency. It depends on a cycle when it gets to that particular devices, depending on whether an event happens in relation to the polling cycle. And finally, security concerns refers to potential vulnerabilities these mechanisms can introduce. Interrupts can be exploited to cause a denial of service attack if needed. For example, a device or a program overwhelms the CPU by flooding it with high priority interrupts. Polling is less susceptible to such attacks, but it might overlook security checks if implementation assumes regular checks are sufficient for detecting anomalies. So you can get into this false sense of security there. Make sure you know a few of these factors to do an effective comparison between both techniques. Now, of course, these are used in real world settings, and we need to know how they impact keyboard and mouse inputs, network communications, disk input and output operations, embedded systems, and real time systems. Now, in keyboard and mouse inputs, interrupts are typically used. So when a key is pressed or a mouse is moved, an interrupt signals the CPU to process the input right away. It provides a seamless experience to the user. Polling these devices would introduce lag and decrease user satisfaction as a result. In network communications, interrupts are also used where incoming packets can arrive unpredictably. So, an interrupt driven approach allows the network interface card to alert the CPU that data has arrived, ensures timely processing, and reducing latency. Disk input and output operations, interrupts are preferred here as well because I/O operations notify the CPU when a read or write operation is complete. So the system can efficiently manage data transfers without constantly checking the status of disk operations. The CPU can then do other things. In embedded systems, such as sensors in IoT devices, interrupts are also used for efficient power management. Since these devices use battery power most of the time, you need to conserve energy, and we already know that when an event occurs, that's when you want to use power. Otherwise, you want to be in your idle state. Polling would require the device to be awake more frequently, which consumes more power and reduces battery life. In real time systems, such as those used in medical devices or automotive controllers like autonomous cars or industrial machinery, interrupts are also used to meet strict timing constraints. In these systems, control latency is critical. System must respond immediately to inputs or changes in conditions because you often have guaranteed time frames to ensure safety and effectiveness. Polling would not work when you need timely responses. In all of these situations, interrupts are key. But it's also possible to use polling in embedded systems and real time systems. That depends on the context. And often hybrid models are also common, combining polling for high speed tasks and interrupts for irregular events. And this is where your device or your operating system will make the decision. Now, in the exam, if you're given a scenario, you will need to read it carefully and then make the right suggestion. So let's look at an example, for example, a game controller. In this situation, you will physically move the control sticks or press a button, which then generates a signal. This leads to the generation of a data packet, which is then transmitted to the console. The process or technique used here is an interrupt signal. The console will then call the relevant interrupt service routine to deal with that interrupt. The data from the packet is then interpreted. The scene movement is calculated. So if you chose to press left, the character has to move left and so on. The screen is updated, the scene is redrawn, and then the CPU resumes its previous tasks. Now, the CPU is always doing something, calculating enemy movement, the artificial intelligence side, and every time you then press a button, the interrupt occurs. It parks whatever it's doing, it deals with the interrupt and movement, calculates it, updates the scene, and then reloads whatever it's doing and carries on. Now, most interrupt based devices would use a similar type of structure. Okay, on screen you will see key terms related to this particular lesson. As always, pause the video and go through them. Make sure you add them to your glossary before continuing. That's all for this particular lesson. Hopefully you know enough to answer the following practice questions. What is the main disadvantage of polling? Why might interrupts be preferred for battery powered devices? In what scenario would polling be more appropriate than interrupts and vice versa if you change that particular type of question? What is an interrupt service routine? How can frequent interrupts reduce performance? If you do have any questions about the content of this lesson, feel free to leave me a comment. Otherwise, I'll see you in the next one.